you about the topic of the electron phonon coupling laser crystal, and it's from Shanghai University. This report contains 5 parts. So first, I'll give some background knowledge of the laser radiation. So about a century ago, the Bohr come up with a hydrogen atom mode, which we can see the electron transition. So the absorption and the emission of light, which indicates, and also the Einstein and his theory of the stimulated emission. When the electron gets absorbed, and it can happen the stimulated emission. One electron can increase to 2 and 2 to 4, and etc. So this can achieve the light amplification and became the theoretical foundation of the laser generation. So like the laser is really important, as we know for this pointer. In 1960, American scientist Mayman used a ruby crystal to get the first leading, and the laser operator is pumped by the Zhang lamp. And after development, we have the non-linear crystal, which can change the wavelength. Nowadays, the laser can use in the scientific instrument, laser medical, and laser application. So the laser, the semiconductor, computer, and nuclear energy has become 4 greatest innovation of the 20th centuries. So basically, there are 2 type of the laser crystals. Well, the first is a normal laser crystal, which can laser in the specific wavelength. The typical is the famous neodymium YAG, the neodymium yttrium-188, and the TIE Spire. This one normally generate near infrared band technology, and also is really mature and has been totally commercialized. And the other type of is a non-linear crystal, which they use a frequency conversion and try to expand the wavelength. The typical is a BBO, LBO, and KTP, which give you from the visible to UV frequency conversion, and this lead to more like the advancement in the crystal. So with I mentioned before, like the wavelength is determined by the difference between the energy level, and also the electron has a intrinsic energy level. So the problem is, can we turn the wavelength of the laser? So we made up a theory. So when we consider the Schrödinger equation of the system, the Hamiltonian contains 3 parts. First is the electron part, which is come from the electron transition. And the second is the phonon part, which because the lattice vibration, and the third part is when the electron interact with vibration, it has an energy transfer. So they have the phonon and the electron interaction, called it the phonoelectric coupling. So here's the equation, and with first we want to solve how the phonon behave in this process. So we use a spectral function of the electron phonon coupling. So this function has 3 parts. First is electronic energy transition. And second, the middle part is quantized phonon energy mode. And the last part is phonon energy and spectral expansion, which determines the position of this spectral function. So next we will solve the phonon part to get to understand the behavior. First we need to combo this two mode, the electron transition mode and the phonon mode, to get our own mode, which is we call the electron phonon coupling mode. And we think this coupling mode can turn the energy level, and therefore to restriction the electronic energy level. So here, in order to understand the phono behavior. We want to get a solution of the phono process. So we use basically we use a harmonic oscillator and plug in to get the answer. So it's clear that we have the every behavior. So the F0, which shows the electron transition, and F2 is the one phonon participate, and F2 is the two phonon participates, etc. And also we have some theoretical spectrum of this participation. So also there's in 1950 there's a Horn's theory also studied the phonon modes, and also in this series they have the Horn's factor and the fluorescence emission spectrum. So the Mr. Huang start from the color center crystal and conclude that the electron phonon coupling is like it's not considerable, and they limit to one single phonon because they think the two phonon and three and more multi-phonon effect is really small, so he just ignores them. So with this Huang's series factor, he indicates the broadwise fluorescence material, which the typical spectral is tight wire. But in our case, when we consider the multi-phonon participate, we have our mode. We use a weak emission from the multi-phonon coupling and plus the strong stimulate emission. So in our theory, we think we can break through the electronic energy level and to extend the spectral limitation. So next is the material selection, basically. So we will also first back to the function. We will solve the Hamiltonian part of the electron phonon interaction, and with the solution we can see there's two parts, which is the function units, which suggests the rho, which is the charge density, and r, which is the radius of the bond, and also the order, which shows the position of how the ions lie. So the material we try to find, which has a large charge density, short bond length, and efficient superposition. That's the aim we try to find. And the typical one we can find is free oxygen. And also with a comparison, we can see the chain overlay is better. And on the right, it shows the fluorescence of the free oxygen. It has a better fluorescence. So with all this, we also use a detector to get this. So the system we choose is a rare earth COB system, and with a free oxygen units and the chain agreement. So next one, we want to select the doping, which is the active ions, also the lasing possibility. So with the Humo-Rose rules, which shows ytterbium is more coupling when doping with the host material. So we select ytterbium YCOB crystal as our lasing crystal. So next, the composition of the ytterbium YCOB is really complex, so it's really hard to grow the high quality and large crystal. So first we need to analyze the phase diagram and then use a computer simulation to guide the process. And then use the crystal spiral growth. Finally, we can get the large and high quality 2-inch crystal. And here are some challenges we have. And also for next step, we need to design the cavity. In our case, we use a code. As a code design, we call two-sided buckle, which is like the the filter. You can select the wavelengths and amplify it. And with design, of the YCOB and the laser design, we finally get the lasing, which from here, I don't know if you can see, from 1110 to 150 nanometers. And we also, to get all the wavelengths and is match our theory before, which shows 3, 4, 5, 6 phonons coupling. So with the result we have here with our result, which fill the gap of this one from 1000 nanometer to 500 nanometers, and then theoretical we can also fulfill maybe from 1000 to 1800 nanometer with all this wavelength achievement. So after the job, there's an interesting review paper called Light in the Darkness. So next, we want to understand which type of phonons can use in this coupling process, and also other maybe the temperature effect of this coupling process. So first, we use this Raman. We have this selection of the. So first, we need to match the Raman activity with this solution, and also with a similar like the Raman selection. So this is basically 2 rules for the phonon participate. And also we consider we have the Curie principle of the laser threshold. With the solution, we found the pump and the temperature. The product of pump and the temperature is a constant. And so in this case, the heat became necessary for laser treatment. So this time we change another crystal. We use a neodymium doped yttrium vanadate to get the similar setup, and also get lasing around 1176 nanometers. And here's the result. Also shows the temperature effect. When temperature increasing, the output power is also increasing. Also here, this result shows the threshold and the temperature is constant. And after we success with the lasing, we put LBO, the nonlinear crystal, to try to frequency doubling and to get the yellow lasing. So compare our result with other yellow lasing, the self-Raman, the efficiency is similar. And on the right also, we have the 1.2 watt yellow light lasing. And with our design, we also can do the turnable lasing with a BF lens. So here's some results we have. And finally, we want to study the time domain because we want to make sure if the lattice vibration can catch the speed of the electron transition. So here the same thing. So this time, so first we need to optimize our laser output. So with the ytterbium YCOB, we get the maximum output power as we can. And then also this is the turnable sighting. So this time we need to select the saturated observer for the Q switch to understand the time domain, because the time domain is relative to the modulation depth, and which also relative to the saturated observer. So first we use a relatively low observer, which is a graphene. So this time we get the leading the Q switch. The time domain is around 237 nanosecond, and also to the 134 nanosecond, which this time the lattice vibration can catch the electron transition. And also we use a more bigger modulation depth, which is a chromium yark. So with this time, we achieved the pulse length of 29 nanosecond. So also with the nanosecond, we can see the lattice vibration can catch up the electron transitions. Here are some results. And here's the outlook. So right now, we are not really fully understand the mechanism of the laser generation. Or maybe in the future, we can also try to get the ultra short pulse and also to optimize the pulse. And also, we provide new material for the nonlinear optics. And maybe with the transition metal and the doping ions, we can get some new lasing materials. And thanks for the Professor Yanfeng Chen and Professor Zheng He from Nanjing University, and the Professor Huanjin Zhang and Dr. Fei Liang from Shandong University, and also thanks their students. Okay, thank you. Any questions?